Okay, let's get into this. Welcome to the deep dive. Today, we're diving into something maybe a bit unexpected. It's the connection between, well, college level math, specifically calculus, differentiation and integration, and the world of forest resources technology.
Right. It sounds abstract, maybe,
Yeah,
but it's really not when you look closer.
exactly. And this deep dive, it's based right on the source material you shared, which really focuses in on how these math tools are, well, indispensable for understanding something vital, like how forests capture carbon.
Yeah, what's really interesting here, I think, is seeing how these concepts, the ones you learn in a classroom, actually give us the tools, the language even, to measure what's happening out there, in the real world, in forests. It helps manage them.
Totally. So our goal here is to sort of unpack how differentiation and integration aren't just homework problems. They're super relevant if you're working in forest resources technology, especially with carbon sequestration. And just for clarity, forest resources tech covers a lot, right? Sustainable harvesting, checking forest health.
Wildlife management, yeah. And the big one now, carbon accounting, climate change mitigation. And a lot of that work needs really precise measurements and, well, predictions.
Okay, so that's the setup. Calculus comes in how? Exactly. Let's start with differentiation, maybe.
Good place to start.
Yeah.
So differentiation, the sources highlight its role in understanding the rate of change. That's the key word.
Okay.
In a forest context, that means figuring out how quickly something is changing, growing, shrinking, whatever, right at a specific moment.
The rate. Okay, so not just like the total carbon locked away in a bunch of trees, but how fast the forest is pulling CO2 out of the air right now. Or maybe how fast a tree is adding wood year on year.
Precisely, yeah. The source material talks about using differentiation to analyze forest data.
Yeah.
You might have tree measurements over time, or maybe data from, say, LiDAR, that's remote sensing, gives detailed structure. By modeling forest growth, or maybe biomass accumulation, as a function, differentiation lets you calculate the instantaneous rate right then.
Instantaneous rate.
Yeah, it's basically finding the slope of the growth curve at that specific point.
Right.
Is carbon capture speeding up, slowing down, holding steady? It tells you that.
Okay, that makes sense. For the speed of capture, the dynamics. But what about, the bigger picture? The total amount, someone managing a forest also needs to know the total carbon stored over, like, the last 20 years, right?
Absolutely.
It's crucial, too.
Feels like the other side of the calculus coin then.
It is exactly that, and that's where integration comes in. It's essential. If differentiation gives us the rate, integration lets us take that rate, or maybe a series of rates, and figure out the total accumulation over some interval. Think of it like adding up all those tiny moment-by-moment changes over time, or maybe across an area.
Ah, okay. So if you figured out the rate a forest stand captures carbon each year using differentiation, integration lets you sum all those yearly amounts up to get the total carbon it's socked away over its whole life, or maybe just during a specific project time frame. It's exactly right. The source material mentions this for forest inventories, carbon models. For example, you integrate the biomass growth rates over the age of the trees, and that gives you an estimate of the total standing biomass.
Which you can then convert to carbon stock.
Yep. Or integrate the sequestration rates over a whole region to find its total carbon offset potential. It bridges from the speed to the total amount.
That connection feels really solid. Differentiation for the how fast now, integration for the how much total. They really work together for accurate modeling, accurate reporting in forest tech. It's not just saying math is used. It's seeing how these specific calculus tools actually let people measure and manage these, well, really important environmental processes you found in the sources.
It really does. It gives you that much richer picture beyond just static numbers. And it shows that the precision we need now, especially with climate science and carbon markets booming, it relies directly on these mathematical ideas, understanding differentiation, integration. It lets professionals move past rough estimates to really quantifying forest health and what it does for the environment. Data-driven.
Right. So wrapping this part up, the core idea from this dive seems to be differentiation nails the rate of carbon capture, and integration calculates the total accumulation. It directly links that abstract math to, well, vital environmental technology practices described in your sources.
Definitely. And that brings up maybe a final thought for you, the listener. Think about this. What other mathematical tools or maybe scientific principles that seem purely academic, where else might they be working, sort of silently behind the scenes in your own world, underpinning systems or tech you use every day, providing these hidden measurements or models? Kind of makes you wonder about the unseen power of these tools, doesn't it?